Section 3.4 deals with velocity and other rates of change. So now we're going to do a little bit of work with applying derivatives. So instantaneous rate of change. As we've talked about, the instantaneous rate of change of f with respect to x at a is the derivative f prime of a found by the limit that we've been using over and over. Any time from now on when we say rate of change, we mean instantaneous rate of change. If they want the average rate of change or the change between 2 points, they will use the word average. So rate of change means instantaneous or a derivative. So an example of instantaneous rates of change. If the area of a square as a function of the radius is a equals, that should not say a square, that should say a circle, is a equals pi r squared, then we want to find the rate of change of the area with respect to the radius, and we want to evaluate that rate of change when r equals 4. So do those two things quickly and pause the video. Okay, so finding the rate of change of the area with respect to r, that's dA dr, or d dr with respect to a. So the rate of change is the derivative, dA dr, which is 2 pi r using our power rule. And then evaluating that when r equals 4, we get 8 pi. Pretty simple problem for rate of change. Motion along a line. If an object is moving along a coordinate line so that we know its position, s, as a function of time, then the displacement of the object is from t to t plus delta t, that's our change in time, is delta s, change in position. It's the distance at t plus delta t minus our original t. You can see that this is just a simple difference of one distance of the one position minus the other position. The average velocity, again not instantaneous, is velocity equals d over t, velocity equals distance over time. Change of s we've already found to be this over our change of t, a simple slope equation for average velocity. Instantaneous velocity is the derivative of the position. So now we're going to add that it's the limit as our delta t approaches 0. Speed is the absolute value of velocity. Again, pause whenever you need to write down what you need to have in your notes. And acceleration is the derivative of velocity, or the second derivative of position. So a body's velocity is v of t, then the acceleration is dv dt, or the second derivative of position. Now, free fall constants, these are ones that you should know. When we talk about feet or meters, both of those are values that you should be familiar with. So what we're talking about here is that g value is the acceleration due to gravity. Our formula for position or distance is 1/2 gt squared, where g again is the acceleration due to gravity, and t is the time that has elapsed. So using this formula, we can come up with two values, one in feet and one in meters, for our free fall constants. So again, an example, a projectile shot upward from the Earth's surface and reaches a height of s equals negative 4.9 t squared plus 120 t meters after t seconds. Find the velocity after 5 seconds. So again, a very simple problem using the derivative of position or of distance to find velocity. So go ahead and find the velocity and then turn the video back on. So hopefully we got that velocity is the derivative. So using our power rule and then evaluating that when t equals 5, we should get 71 meters per second. Okay, so some pretty simple examples applying those derivative rules to velocity and acceleration. All right.